Thank you everyone for joining in today. I've been looking forward to doing this webinar as I've watched the interest of using methods like atom probe tomography and other microscopy techniques like TEM or X-ray microscopy. They've been rapidly growing in the field of earth sciences. So it's great to be able to share some of the workflows that we use here at CCM to study different types of geologic materials, whether they be ore deposits or meteorites, and begin to kind of push what information we can learn from them. And for anyone tuning in that is not necessarily studying Earth or planetary materials, the workflows I'm showing here can be applied to many different areas, including semiconductor or biological materials. So there still should be something useful that you can learn from today's webinar. So I want to start off by first acknowledging my title, Planetary Records Down to the Atom Scale, which originates from this book, Microstructural Geochronology. So this monograph was the first of its kind, and it highlights different techniques that can be used to measure and interpret the history preserved in minerals at the micrometer scale all the way down to the atomic scale. And if you're not familiar with the term microstructural geochronology, this basically represents the way we gather this information, which is by combining two areas that geologists commonly use for studying minerals, geochronology and structural geology. So geochronology, more specifically isotope geochronology, is a benchmark method that investigates the isotopic composition of elements contained in minerals with the aim to better understand the geologic processes that they underwent and the timing that these events happened. So for example, we can use naturally occurring radioactive isotope systems, such as uranium-lead, or neodymium-samarium, or potassium-argon, just to name a few, and these can be used to date the mineral. And this is done by looking at the ratio of the parent and daughter isotopes. So if we look at my gray minerals here, right, the green dots represent our parent isotope uranium. And over time, these uranium isotopes will decay to our orange lead isotopes. So at present day, we can measure the ratio of uranium and lead and see how much time has passed, which tells us the age of the mineral. On the other side, we have structural geology, where we can study the structure and textures preserved in our rocks and our minerals. And this can be done from field measurements at the micrometer scale, or we can use the SEM and different detectors on the SEM, like our EDS and our EBSD, to study these structures and these phases in our rock at micrometer scales. So you can see from this meteorite example here that these textures can be quite complex, right? Here we see different growth textures. We see fractures that have been likely infilled by melt, and we have lots of cross-cutting relationships. So by combining these two areas, we can study the structures that we see here and then specifically choose certain minerals or parts of the mineral that we want to date using geochronology. And then together, this gives us a fuller context of our sample and the environment in which it formed and the different events that it went through throughout geologic time. So now that we've defined microstructural geochronology, we can use it to study planetary materials, whether that's analogs from Earth, or valuable meteorites, or samples from return missions from, let's say, Mars or the Moon. We want to be able to gather as much information from these samples as possible, from both a planet scale right down to micrometers and nanometers. And for this, we need a workflow that includes many techniques that range in their resolution. So here's an example of such a workflow. On a large scale, we can study planets directly by mapping them using satellites and rovers. And then we can take pieces of these rocks and non-destructively characterize them down to micrometer or even sub-micrometer scales using techniques like X-ray microscopy or electron microscopy. And then more traditionally, these can be paired with secondary ion mass spectrometry or thermal ionization mass spectrometry to gather our compositional and isotopic information. However, more recently, higher resolution techniques like transmission electron microscopy or atom probe tomography have really grown in popularity. And this is given that they can contribute to this workflow by allowing us to push our spatial and elemental sensitivities into new territories. So you can see from this plot here that Atom Probe actually fills a really interesting space between TEM and SIMS in that it combines parts per million elemental sensitivities with nanometer scale spatial resolutions, and therefore opening up a whole new range of information that can be explored. So building off that brief introduction, I've decided that for today's webinar, I kind of want to break it up into two areas. The first will highlight the correlative workflow possible here at CCM that can be applied to studying geologic materials, and I have a really cool meteorite example to show this. And then for the second part, I want to show more specific Atom Probe related examples, which hopefully will help highlight the strength of putting Atom Probe in our workflow and helping push us down to the atomic scale. And I've chosen a few examples covering both planetary science and then more economic geology. So now let's take that and jump into our first part and look at a workflow possible at CCM. So you might recognize the slide as I've shown it before, and I like it because it highlights the correlative capabilities here at CCM that go hand in hand with our APT research. And if you take anything from it, I want it to be that we have a wide range of instruments that allow us to characterize materials from centimeters right down to the atomic scale. So for example, we can start on the left using our scanning electron microscopes or our X-ray microscopes to begin characterizing our sample. Then we can take our sample to our ion microscopes or our FIBs and use these to prepare our sample for our higher resolution analyses like the TEM and Atom Probe. And thanks to correlative holders and our cryo and vacuum suitcases, we can go back and forth between these instruments under different conditions following different pathways. And you can see there's a lot of pathways based on all the arrows. And if you aren't familiar with any of these instruments, I strongly recommend you check out our YouTube channel, as most of these have been covered in detail in other webinars. But for this webinar, I just want to focus on the workflow in detail, and this starts on the left with our initial characterization. So our SEM, FIB, and XRM instruments act as good starting points for initially characterizing our sample. The SEMs allow us to characterize our surface, and many times we can identify a feature of interest and then use the FIB to further prepare our sample for TEM and Atom Probe right away. Or we can add XRM to our workflow and now see the internal structure of our material. And when you pair them together, you get a whole new perspective of your sample. So for example, these images are from newly published work done here at CCM, characterizing human bone using XRM, laser FIB, and our plasma or PFIB, which provides a highly resolved structure. And what you will see in my following slides is that we can use this correlative information to identify internal features, like this blue piece here, target them, and then prepare them for Atom Probe and TEM. And a cool tool here at CCM that allows us to do this detailed characterization of our surface while correlating it with different types of information, like our X-ray data, can be found using our Zeiss Crossbeam. So if we take this image of Simon as an example, we can broadly see what he looks like and the environment he's sitting in. But it would be nice if we could just choose any area of this picture, zoom in, see more details while maintaining the resolution we want, such as zooming in on his bow tie and seeing the polka dots. This is a capability we have at CCM using our Zeiss Crossbeam SCM Fib and our Zeiss Atlas V browser-based viewer. This software provides us with a space where we can bring together images and data from multiple instruments, so light microscope, SEM, XRM, and bring them all into one spot to produce a single picture of our sample. And then this aids in allowing us to better correlate features that are visible across these different sources, across these different length scales, and put it all into one spot, and then we can share this data easily with collaborators. So here on the right, we are looking at the surface of a meteorite that we've mapped in the SEM using both secondary electron, which is shown on the left, and backscatter, which is shown on the right. And as you can see by the scale bar, this is a pretty big area. So the field of view is around 2 millimeters by 1.5 millimeters. So if we wanted to image any of the small features here, we'd have to zoom in to specific areas, focus, take our image, and then repeat this process over and over again. And if this is a new sample that's full of lots of grains and lots of textures, like most meteorites are, you may not know what features are in your sample until you've kind of stumbled upon them. So you could be on the SEM for a long time, taking pictures. So by using the Atlas V software, we can use an automated process to take a large number of images at different resolutions and using different detectors, and then stitch them all together to create a large interactive map of our surface. And then this can be analyzed in detail later when you're off the SEM. So similar to Google Maps, we can zoom into features of interest in different locations while maintaining the resolution we want. So here we've zoomed in on what look like 3 large clasts, but now we can see that they're actually comprised of a lot smaller rhomboid structures. And depending on the data that we've stitched together, we can zoom in even more, and now we can see submicron textures of the matrix. We can see different textures and sizes of the rhomboid grains themselves, and we can see that there are even some smaller submicron structures. So in a way, I've created kind of like a guided tour through my data where I can quickly zoom in and out to different length scales, gather whatever spatial context I need, and can do this at any position in my sample. I can also highlight key features of interest, such as my target locations, which I can use for future correlative work, like taking an atom probe liftout or making a TEM lamella. And at any point, I can come back to these locations and study them more if needed. And since this data is exported into a web-friendly form, and I'm viewing it in a browser-based viewer, I can now easily share this large amount of data with collaborators, allowing them to jump right back in, zoom in around the data, draw their own conclusions, leave comments, and make annotations for me to see. So this is a very quick glance at this feature, but you can visit Petapixel Project to view and interact with a number of very cool data sets. And these range from metals to semiconductors to biological materials to geologic materials. And they were all produced using the Atlas V browser-based viewer toolset. So I definitely recommend to go check it out. Okay, so now that we've characterized our meteorite surface in detail, let's take a look at the internal structure using XRM. So using our Zeiss Versa 630, we did 2 scans of our meteorite. The first was of the entire sample, which we can see here, so it's centimeters in size, and this provides us with some initial context. Our resolution is lower with this initial scan, but taking slices through the dataset, we're able to see that the rhomboid clasts, which are similar to those at the surface, are pretty homogeneously dispersed throughout the volume and that they range in size. And since we could identify those three clasts at the surface with our first XRM scan, we're able to then conduct a smaller subvolume scan of that area, which I have shown here in red. And now this provides us with higher resolution data. So this video is showing a slice-by-slice progression through the volume, and we can now better see the distribution and sizes of the clasts. We can also see other internal features like annealed and open fractures. We can see how they propagate through the data, and we can see the distribution of clasts relative to these features or these fractures. So overall, this is providing us with kind of out-of-plane context, which we wouldn't get with our traditional SEM or FIB cross-sectional image. Okay, back to our workflow. So now we've imaged our surface, and we have a better context of the interior of our sample. So now we want to correlate this data together. And if you remember what I said a couple slides ago, this can be done back on our Crossbeam, again using our Atlas V software. So back on the Crossbeam, I've taken my backscatter image of the surface and overlain it with my XRM data. And if you visit the Pixel Project website I mentioned, you'll see examples of this being done using multiple sources, such as different SEM detectors, light microscope images, or even optical images such as something from your digital camera. So in this case, I've annotated a green box that represents my target liftout that I want to extract from the surface. And by correlating my two data sets, I now know my liftout will contain a feature of interest at the surface as well as internally, right? So here we can see this class at the surface, and then we can see this large internal cluster here. And this image doesn't show it well, but we're able to know the exact depth of this internal feature because of the XRM data. And now this gives me the option to do further preparation of either of these features, surface or internal, so that we can do more characterization using our high resolution techniques like TEM and AtomProbe. So let's start with the more traditional route and look at doing a surface target. So for targeting a surface feature, this is a Framboid class imaged using the SEM. We can move forward by taking a standard liftout for AtomProbe using the FIB. So this is done by milling our trenches to form our cantilever bar, kind of like a Toblerone bar with a triangle bottom. We can extract this using an in situ micromanipulator. We can attach this liftout to individual silicon posts and then use annular milling to make them into needle shapes for AtomProbe. And I don't have it shown here, but we can also take a traditional cross-section or surface liftout for TEM as well. So anything we can do from the surface. So you might be wondering, okay, why did I go through all that effort to collect XRM data and correlate it with the SEM surface image if we're just going to target a feature on the surface anyway? Well, again, it's all about context. So if we look at the man in the boat, it looks like he's having a nice paddle. But a look inside the water says that he has some visitors. So it's the same idea with our sample. Knowing the 3D structure of our feature of interest and the surrounding matrix material and fractures and other clasts only help us with our final interpretation of the results. And this idea of gaining out-of-plane context is often used. So this example here, we use the complementary nature of 3D FIB sectioning with more conventional EELS and APT analysis, and we're able to see the propagation of the oxidized grain boundary in a nickel 600 alloy. So in this situation, if I take my liftout for AtomProbe at this location, is my tip on one end of the liftout going to capture the same feature 15 microns away at the other end? And if our boundary is propagating like this, it's not going to be the case. So it's the same idea with the XRM data in that it provides us with the same context to kind of guide the preparation of our liftouts for AtomProbe and TEM. Okay, so we've looked at targeting a surface feature, so now we can look at the alternative route where we target an internal feature at some depth in our material. And this feature would not normally be accessible, or it'd be very hard to target trying to use our traditional FIB procedures. But luckily, we have access to a laser FIB and our Atlas V software. So if we come back to our correlative map and decide we want to target this large internal class, we need to make it accessible, meaning we need to be able to extract it from the sample. And this can easily be done using our femtosecond laser, which is added to the airlock of the crossbeam FIB. And this provides efficient site-specific extraction of relatively large volumes at orders of magnitude faster than conventional ion milling. So using the laser, we can quickly prepare large trenches. So this example here, our lift out's about 350 microns by 70 microns and about 100 microns deep. And the laser ablation process for this took only a few minutes. So once this is done, we can then take it to the PFIB and use that to create an undercut, extract it from the surface, and then attach this large volume on top of a custom grid. And this is also an advantage of the laser system, is that we can create these custom grids, which can then be used across different instruments for different purposes. So once we have our block lifted out, the goal is to be able to transfer it around the center to different instruments depending on what high resolution information we want to obtain. But to do this, we need to develop a workflow. So this schematic is an example of one that we used for our meteorite sample. And you can see that it goes kind of across several instruments. So our XRM, our TEM, our atom probe, our FIB, and I would argue that it starts with one of the most important things, which is our ability to transfer the sample around without damaging it. Because we know that there's nothing worse than working on a sample for days just to then bump it or drop it. Our solution to this was working with the Ultrafast Electron Imaging Lab at the University of Waterloo to design and manufacture a custom half-grid holder, shown here. And I've talked about this holder in my previous webinar, and where it shines is that it allows for the efficient cycling between our Talos 120 and our Talos 200 TEMs, all our FIBs, our XRM, and the LEAP, all without having to touch the half-grid during transfer, which greatly reduces the risk of damaging our sample. It can also hold a range of half-grid sizes, from our standard 30 micron copper grids to custom thicker grids that we can make of any material using the laser. The image on the right are one of these custom half grids. I believe it's an aluminum grid that was sharpened using the laser, and then a final FIB step was used to just produce a flat top that mimics the more standard silicon post. So this makes sample prep as close as possible to our traditional kind of routine, which is always a good thing. So using these custom grids is convenient because their thicker size make them easier to load into the holder, and then once they're in the holder we don't have to touch them, and the holder can then go to all our instruments with ease. Okay, so back to our schematic. We have our correlative holder. It's holding our meteorite, which we've extracted using the laser and attached to a custom grid designed for XRM. So now let's collect more XRM data, but with higher resolution this time. And here it is. So again, we have our 3D volume, where we can take X, Y, and Z slices to view any point within it. And with this resolution, we can now better resolve the shapes of our smaller clasts and even begin to resolve some of the smaller grains within these clasts. And this is because we've mounted our sample block onto our custom half grids that are designed to enable an unobstructed 360-degree view and allow us to bring the detector of the SRM closer to our sample. And the benefits of having our sample as a protruding block is that we can now either target the top of the block, or we can rotate it 90 degrees to target the cross section. And if you remember, our block was about 100 microns in Z. So this means that we can target buried features down to this depth, which were not accessible before. So taking a look at the data, we previously said we wanted to target this internal clast, which we now can see is comprised of a lot of smaller framboids, which would be perfect for targeting for TEM and Atom Probe. And to target it, we can use the pfib to mill top down into our sample until we reach this internal plane. And we've measured this distance from our XRM data, so we can mill this, and now it becomes our new surface. And we can compare our XRM data with our SEM images of our new surface. So we know that we've milled into the block the correct distance, and we've reached our target. And now that this plane is our new surface, we can image it in more detail with the SEM and map out our exact locations for TEM and Atom Probe. And at this point, we can also study the new surface in detail using other detectors. So here we're seeing our EDS maps of several elements, and we can see the framboids have a different composition than our surrounding matrix. And then we can also do this using, let's say, EBSD or CL, depending what we want to achieve. So it just, by creating a new surface, we're able to gather a whole new set of information from our once internal feature. Okay, so to summarize, up to this point, we've identified our feature of interest, we've studied it in 3D using XRM, we've targeted it using the laser fib, and then we've further characterized it, again using SEM and EDS. So now we can kind of push to that nanometer scale and collect our TEM and Atom Probe data from our once buried feature. And you can see from my schematic here that it doesn't have to be as simple as just doing one or the other, that we can actually do correlative TEM and Atom Probe to gather even more information than traditionally. And here are those results. So for TEM, we were able to prepare a standard surface lift out from the block, and now we can see even the smallest of our individual framboid grains with more detail, and we can see the variations in chemistry within these grains and the material around them. And since we collected EDS of the surface in the SEM, we can compare those results with our STEM images here. For APT, we can prepare a traditional lift out from our new block surface, and thanks to our correlative holder, we can take TEM images of our tips prior to doing Atom Probe, which aids in confirming the presence of the boundary in our final tip, which we can see we've captured here in our final spinning reconstruction. And since we've done our correlative workflow, we can compare the chemistry of our grain boundary across the Atom Probe and TEM data. So that's all the details I can really go in right now about these results, but I do have a published example of a similar framboid that I'll talk about in a bit. But I do hope that these results help highlight the strength of doing correlative work. So from our Atom Probe data, we can see our grain boundary, and we can see that it's decorated in a number of elements. So having context of the surrounding grains, their textures, and their chemistry, by using EDS on the micron scale and nanometer scales, this only aids in our interpretation of our final APT results. So that wraps up part one. So now that I've shown an example of a workflow for studying geologic materials that spans across a number of instruments and different resolutions, I'd like to now focus down to the atom scale and show some examples where APT data provides us with records of past geologic events and their timing. So this relates to our microstructural geochronology. And then I've also thrown in some examples looking at native minerals and our deep geologic repositories. So this is a picture of Earth as we know it, with liquid water oceans and an oxygen-rich atmosphere. This is an artist's rendition of early Earth, more than 4 billion years ago, a period referred to as the Hadean, and you can see it's believed to be a much more intense environment. However, during this period, there is some evidence that suggests that temperatures were low enough for liquid water to exist on the surface, making it much more habitable. In this second scenario, the rate and distribution of meteorite impacts would play a significant role in establishing the crustal conditions that are suitable for life, and this rate is predicted by modeling to be quite high. However, almost no geologic record from this period remains, but insights can be gathered by studying nearby bodies such as the Moon and Mars, where ancient crust does persist, and we can compare this with what we know on Earth. And a part of the geologic record, which we can compare between Earth and Mars, are the zirconium-bearing minerals zircon and bdelliite. These are highly refractory phases, with zircon crystallizing from silica-saturated melts and bdelliite from silica undersaturated melts, so our basaltic magmas. Chemically, these phases are rather simple. However, they do incorporate minor and trace amounts of important geochemical tracers, and this includes uranium. So if you remember, uranium is incorporated into our minerals lattice, and then over time it decays to lead. So assuming that this has remained a closed system, we can take a ratio of our uranium and lead and determine how old these minerals are. So you can imagine that the strong nature of these phases and the extremely sluggish diffusion rates of trace elements, including uranium and lead in our rare earths, it makes these grains the ultimate survivor minerals, as they can preserve robust records of chemical, isotopic, and microstructural information that are useful for reconstructing the evolution of early planetary crusts. So relating this to Atom Probe, the pioneering work on zircon was done by John Valley, who looked at one of Earth's oldest zircons, which is dated at 4.4 billion years old, so very old. These zircons showed that the radiogenic lead, so the lead that was produced from the decay of uranium, which was originally incorporated in the lattice, was not homogeneously distributed, but instead segregated into clusters, which you can see here. And this was together with yttrium. And since we can distinguish different isotopes with the Atom Probe, what they found was that they could measure the 207 lead versus the 206 lead incorporated in the clusters. And this ratio could actually be used to constrain the timing of a younger disturbance at 3.4 GA. So looking at this plot, the ratio of lead is actually the slope between these two ages, so 4.4 and 3.4. And this segregation of lead and other elements that are incompatible to the zircon lattice have been reported in a number of metamorphically heated grains. It has been also demonstrated experimentally using crystalline unheated zircon that these trace elements remain homogeneously distributed, while when we heat the zircon in the laboratory at around 1400 degrees Celsius for 24 hours, we now see dislocation loops in our grain that are decorated with these trace elements, including lead. So these results are actually very important because the identification of these clusters in our Atom Probe data of zircon can now serve as a proxy for high temperature disturbances in old grains. So with that idea, we wanted to look at another environment where we would expect evidence of high temperature disturbances to be preserved in our zircon grains. And what better environment than a shocked zircon from the center of a giant impact crater. So we selected 2 target grains from near the center of the Red Fort impact structure in South Africa, which is one of Earth's largest impact structures. And this one's had a crater diameter of 250 kilometers and crustal rebound from depths of 15 kilometers deep. So typically, a zircon that has experienced the shock wave compression and rarefaction stages of an impact, which you're seeing in this video clip, will contain a progression of shock microstructures that vary with shock pressure, temperature, and duration of the thermal pulse. And these include planar features resulting from the initial shock compression, followed by the generation of microtwins, annealed curvy planar fractures, and melt glass inclusions, all which form during the shock rarefaction stage. And then this is followed by zircon recrystallization and some plastic deformation that's associated with post-impact modification and heating. And linking this back to uranium-lead geochronology, this microstructural progression has been shown to correlate with partial to complete lead loss. And we know lead loss, so lead being removed from the system, is going to affect the ages we measure because it's not a closed system anymore. So here, we can identify and map out these structures in the SEM using different detectors like our backscatter, our EBSD, our CL, and compare it to our uranium-lead SIMS ages. And this information altogether can help us determine the temperature and pressure we believe our zircon had experienced. And then using this information, we wanted to select atom probe data from an area that was intersecting these shock-related planar features that seem to be associated with lattice rotations of up to 8 degrees. So this is our plastic deformation. It's also in an area that we see a network of annealed curvy planar fractures, some that host impact melt glasses. So this is indicative that we've reached higher temperatures. And as expected, given the high temperature history of these grains, our APT data does contain 10 nanometer diameter clusters of aluminum and lead. And what's interesting is the lead is not supported by the parent uranium. And looking at the clusters a bit closer, we can measure an average lead ratio, so our lead 207 over 206, and this ratio is about 0.5. And like with John Valley's work, although this lead ratio doesn't represent a meaningful age, the ratio strongly fits a theoretical value for a grain that's 3.4 billion years old that had lead forming inside the lattice for about 1.45 billion years. And then at 2.2 billion years ago, we had our Vredefort impact, and the high temperature and shock from this allowed lead to become mobile and then segregate to these clusters. So our results represent an important nanoscale proxy, again for high temperature shock metamorphism, which in the presence of well-characterized shock microstructures can be used to identify and date these relic bombarded crusts, not just on Earth, but other planetary bodies as well. So this means we can apply it to places like Mars and the Moon, which is exactly what we wanted to do for this next study. So this next rock is part of the Martian Paul-McBreshan meteorite family, and these are recognized as a rare sample of Martian regolith. So this is another word for a layer of rock fragments that cover the surface of a planet, also meaning that this meteorite has a chemical composition that closely resembles the bulk Martian crust. And as you'd expect with it being a regolith, it has a widespread lithology that consists of melt rock fragments, sedimentary clasts, and igneous fragments, which include some of our ancient zircon and bedelliates. And all these pieces are set in a fine-grained crystalline matrix. So it's a very complex texture. And these components were likely swept up and deposited by atmospheric rainout after an impact event or events that then lithify to form the meteorite. So overall, it represents a really unique opportunity to study the near surface of Mars. And of course, I had to throw in a cool image of the Martian surface taken from the Perseverance rover. So taking a closer look at the meteorite, we observed some of the oldest known planetary zircon and bdelliite at over 4.4 billion years old. And these grains have shown to record at least two periods of secondary alteration to date. The first being a thermal event, which was around 500 to 800 degrees Celsius, that likely coincides with the formation of the breccia. And then this was followed by a second, much later, low temperature event. And then finally, the meteorite was launched to Earth around 5 million years ago. But what's interesting is that through close inspection of around 121 zircon and bdelliite grains from 5 different polymic breccia meteorites, we looked at backscatter images, CL images, EBSD measurements, and we see in 97% of the grains either weak or no shock metamorphic features and no thermal overprints from shock-induced melting. And this is in contrast to about 80% of the grains studied from bombarded crusts on Earth and the Moon, which show these features. So there's not a lot of evidence for these shock metamorphic features on early Mars. And based on our terrestrial zircon measurements in the Atom Probe, we would expect to see evidence of trace element mobility in these oldest igneous grains if they were exposed to these high temperature metamorphic conditions. But we don't. So the Atom Probe data we collected is therefore in agreement with the lack of shock metamorphic features that we observe at the micrometer scale. So what is the significance of these results? Well, it highlights the strength of using, again, our correlative measurements, right? So micrometer and nanoscale meter measurements, which can be taken from a very small amount of sample, which is important when we're dealing with very valuable meteorites. And it can provide us with insight on a larger planetary process. So in this case, our zircon and bdelliite, these records argue that the giant impact, which is proposed to have created the Martian hemispheric dichotomy, this must have taken place more than 4.48 billion years ago, and then we had to have had a monotonic decline in the impact activity very early in Mars's history. And this is important because it has implications on when the Martian crust could have become habitable. So it has implications for these models. And I just want to point out, so this work was led by Des Moser from Western University, and it was published in Nature Geoscience. So definitely check that out if you want to read more about this study. Okay, so moving on. I said that 97% of the grains in the last example showed weak or no shock metamorphic features. But what about the outliers that do show evidence of alteration? So this is an example of one of those grains. So it's a bdelliite zircon bimineralic clast. So it means the zircon and the bdelliite are kind of one assemblage. And they appear to be part of a larger clast. So I've indicated this by the blue arrows. It's a bit hard to see. And this clast has a larger grain size relative to the surrounding matrix material. And this clast also shows a subophytic texture. So we can see in this white dotted box are plagioclase lats and pyroxenes kind of intergrown together. And this texture suggests that this is likely a clast-laden melt rock. So we have a clast inside the matrix. So taking a closer look at the bdelliite zircon clast, the bdelliite core is surrounded by an approximately 15 micrometer wide reaction rim of metamorphic zircon. And this rim is characterized by smooth embayments into the bdelliite, as well as a zircon-filled fracture cutting across the bdelliite. Focusing on the bdelliite core, we see a blue-green CL emission, which is typical for igneous bdelliite, and we see this elemental zoning in most of the ancient bdelliite grains within this sample. So it fits the population of grains that we see. And then we also see changes in lattice orientation. We can see this looking at our band contrast map. So band contrast is just a quality factor that describes the average intensity of our Kikuchi bands proportional to its crystallinity. And here we can see basically multiple generations of relic twinning. And we can better highlight this using our Euler map and our pole plots. So on the right. So this map highlights that we have magmatic twins, and then these appear to be cross-cut by a second generation of metamorphic twins. And then all these are overprinted by this mosaic of interlocking twin domains that seem to form orthogony related groups of crystallographic orientation. And this is typically indicative of either high temperature or high pressure phase transformations, and then reversion back to our monoclinic structure. And then our zircon rim indicates a reaction of the bdelliite with a silica-rich melt. And when we compare this to laboratory ceramic experiments, such as the growth of zircon within an yttria-stabilized zirconia in the presence of a molten-bearing alumosilicate melt, this reaction is occurring at around 1200 or 1300 degrees Celsius on the scale of hours. And then in natural terrestrial settings, we see reaction rims of zircon around bdelliite with the same type of morphology as our sample that occur with temperatures greater than 800 degrees Celsius. So this is our kind of regional metamorphic high-grade setting. And then looking at the APT data of the rim, we see an inheritance of iron, and this is most likely from the precursor bdelliite. And this tells us a few things. First, it suggests that we had a rapid replacement reaction from bdelliite to zircon, and this must have happened in a short time interval, or else we would expect that this excess iron would be removed from our system instead of being incorporated and trapped in the zircon. And then the clustering of the iron suggests that this was likely a high temperature process. And this abbreviated high temperature reaction is possible given a scenario where the bdelliite grain is, let's say, briefly encapsulated in a high temperature silica magma of either endogenic or impact origin. And again, this example shows how a combination of electron microscopy and atom probe, they really complement each other and provides us with a fuller story of this past planetary scale event preserved in these grains. So the last two examples showcase traces of high temperature environments preserved in our minerals, but what about lower temperature alteration, like with fluids? So this image, which likely looks familiar, this is the Tagish Lake meteorite. So it's a highly brush-shaded carbonaceous chondrite, having minimal terrestrial alteration following its retrieval. So it basically represents a unique piece of the asteroid belt that's ready for us to study. And these really cool grains are actually three-dimensional assemblages of interlocking magnetite crystals, also referred to as framboids. And what makes them of interest is that they form within isolated droplets of water on the parent body, requiring intensive fluid interaction. And it has been proposed that nanometer thick amorphous boundaries or layers around these assemblages contains residue of the parent fluid. And our atom probe data, which you can see here, confirms this. So in our data, we can see this curved boundary, most likely a subgrain boundary between two magnetite framboids. It's about 30 nanometers wide and contains elevated abundances of manganese, magnesium, calcium, and sodium. And this tells us that these grains likely formed within a sodium-rich alkaline fluid environment, and shows that the atom probe is actually a great way to study the remnant residue of these parent fluids in planetary materials. So this work was done at CCM and published by Lee White together with the ROM, and it's published in PNAS, so I definitely encourage you to give it a read if you want to learn more. Switching directions into more of an economic geology example, looking at natural gold. So being able to study the distribution of trace elements in gold is critical for understanding the processes responsible for the formation of high-grade gold deposits, which will ultimately affect our exploration models and processing. And Atom Probe can help us answer questions related to this, such as what major and trace elements are associated with the natural gold, and how are these distributed within the gold. So for this, we selected a piece of gold from the McLaughlin deposit, located in the Knoxville mining district of the Coast Range of Northern California. And this deposit is relatively young, so around 2.2 million years old, and it's an epithermal hot spring deposit. And looking at the Atom Probe data using something called nearest neighbor distributions, which basically measures the interatomic spacing in the immediate vicinity around each atom, which in this case we're looking at gold or silver and mercury. And this shows a direct match with the calculated distribution from randomized data, which suggests that these elements occur in a randomly distributed solid solution. And this was also the case for copper, which was measured in another sample from a different mine. However, this was not the case for antimony, which we can see first in the reconstruction looks like it's forming tiny clusters, and then the nearest neighbor profile is notably different from that of the randomized data, with a clear shift towards smaller distances. So these results are interesting because they can tell us more about the substitution of these elements into the gold. So natural metals like gold are dominated by metallic bonding with shared electrons. So the distribution of silver and mercury being homogeneous, and the fact that the metallic radii of silver and mercury are within 5% of gold makes substitution permissible. Copper has a metallic radius that is around 11 to 12% smaller than gold, but it still can substitute into the gold. The incorporation of copper in gold is well known for imparting increased hardness properties, which is likely attributed to the distortions it creates when it's substituted into the gold. And then we have antimony. So antimony-bearing minerals are common to many gold deposits that can form in a variety of temperatures and depths in the crust, but are more commonly found in shallow, low temperature deposits. So the antimony within the McLaughlin gold is forming nanoscale domains that are heterogeneously distributed, and the metallic radius of antimony is just over 15% larger than gold, suggesting that it's too large to substitute within the gold lattice, or if there was antimony substitution, it has subsequently been migrated into domains through secondary processes. So this work was led by Kim Tate from the ROM, together with the Ontario Geologic Survey, and can be found in the Canadian Journal of Mineralogy and Petrology if you want to read more. And for my final example, I want to show you the use of Atom Probe for studying the corrosion resistance of electrodeposited copper, which is used as a barrier for nuclear use fuel containers, or UFCs, which are used in Canada's deep geologic repositories for disposing of high-level nuclear waste. And as you can probably assume, we need these used fuel containers to persist for hundreds of thousands or even millions of years. So it's important to study the changes in the copper microstructure due to the incorporation of trace elements or oxygen along these structures, and their role in acting as precursors for further corrosion phenomena. So in this study, published in Materials and Corrosion, we used the FIB to prepare atom probe needles from electrodeposited copper, and then used TKD, so transmission Kikuchi diffraction, using our house-made correlative holder. And we use this to track a boundary and confirm its presence in our final sharpened APT tip. And the atom probe data shows clear evidence to support that there is segregation of oxygen, which may be in the form of oxygen or copper oxide at the grain boundary, and this might be happening during the deposition process. And this segregation of oxygen may have no effect on material performance, or it could be important for both high temperature and corrosion performance. So this work was kind of the first steps and is mostly qualitative. However, it's important as oxygen at this level is not visible by most other characterization techniques, but can be studied by the atom probe. It also shows the benefits of adding atom probe to a microscopy workflow. And in this case, we could, let's say, do in situ mechanical testing to target cracking along a grain boundary, and then target that specific boundary using TKD and then atom probe. And where this work links with geologic materials is that we can use natural analogs, such as natural copper, to study these systems, as natural copper can exist intact for millions of years. And the data shown here was collected at CCM as part of the PhD project of Emily Landry from the ZAP lab at Western University. And they are looking to characterize the texture, mineralogical associations, and strain history of the copper. And they're doing this using a workflow of multiple instruments such as EDS, EBSD, XRM, and atom probe. So a cool example is seen on the right, where we actually observe silver and copper phases mineralized together. So using the FIB, we actually targeted this contact and captured it in our final APT tip, where now we can study this boundary with high spatial resolution and elemental sensitivities and see if there is any type of segregation or diffusion across this boundary. So I'll finish up here with a final slide summarizing today's webinar. Hopefully you're able to see the benefits of correlative microscopy for studying geologic and planetary materials using workflows that span across different resolutions. And at CCM, we are always looking to push this workflow into new areas to gather more information from our samples. And depending on your sample, we are always happy to chat about what parts of this workflow, whether it's all the steps or just a few, may work best for you. And then in the second part of my talk, I hope that my examples help show the strength of using atom probe for studying geologic materials, as it can provide us with records of geologic processes that are hidden at the atomic scale. And with that, I'll say thank you for joining today.